Thank you. Let me first tell you the setting. So G will be a semi-simple group. And I will assume that it has only finite center. And the rank of G is at least 2. In fact, I will assume that rank of every factor of G is at least 2. So this is semi-simple. Every simple factor of G has rank 2 or higher. And gamma is a lattice inside G. The G mod gamma has only finite volume. So the basic example is G is SLNR, and gamma is SLNZ, and N is at least 3. Okay, when SL2R has rank 1. So I want to remark that I'm not considering, for example, G is SL2R cross SL2R, and gamma inside G is an irreducible lattice. Even if Margulies superrigidity holds for such lattices. Okay, so assuming this, then G and gamma has nice properties. Let me start with Margulies rigidity. Actually, for this, you don't need such strong assumptions, but it's definitely true in this case. If G gamma and another pair G prime gamma prime are such pairs, then and gamma mapping to gamma prime is an isomorphism, then it extends to an isomorphism between G and G prime. Up to some minor modification, a central defect. So the central defect comes from this finite center. Okay. Then after this, you have superrigidity instead of rigidity. That is, you no longer require the map to be an isomorphism, just a group homomorphism between two groups. Superrigidity, which again does not require such strong assumption. For example, it holds for this case, but I will state it for that. That is, if gamma and G are as such, and you have a morphism into another group, which let's take the linear group, so it's a continuous representation, then this must extend to a representation of G. Again, up to some minor modification, up to some bounded defect. I will not explain this part here. And since G is semi-simple, its representations are well understood, and this is a very nice algebraic object. So this theorem motivated Zimmer to put forward the which aims to understand the following. If we further replace this group by a more complicated group, which is the diffeomorphism group of a compact manifold, then what happens? So what happens to this? It's a group morphism. So does it extend to something? I will not write. Well, sometimes that just does not extend. Okay. What can it be? Okay. So in other words, what's this? So in other words, how can gamma act smoothly on manifolds? And the hope is, like in those situations, there are not many ways for gamma to act. It can only act in a very rigid, very algebraic way. Yeah, that's, of course, I believe it's the truth, and you will see that in many cases it's the truth. Okay, so candidates for gamma actions on smooth manifolds. First, you can act on Néel manifolds. Actions by Néel manifold automorphisms. The basic example is the action by SLNZ on the N torus. So this is the automorphism group of the N torus. In general, the manifold will be N modulo lambda, where N is a nilpotent Lie group, and lambda is a lattice inside N. And this alpha will be a map from G to the automorphism group of N. So all the maps, so automorphism of N as a Lie group, smooth maps that preserve the group structure, and whose restriction to gamma sends gamma to the automorphisms of lambda. Then this makes alpha an action by gamma on the Néel manifold. Okay. This is the first kind of candidate. The second kind of candidate is left actions on quotients on G mod H. Sorry, not. Let me write something else. H mod L. So rho will be a map, a morphism from G to H, and L is a subgroup of H such that the quotient is compact. And the action alpha is, so alpha, a gamma action on H mod L such that alpha gamma acting on H times L is the left translation by the image of gamma and the rho. It's defined naturally, and the basic example for this type is the action on the projective space. So SLNZ is a subset of SLNR, and SLNR acts on Rpn-1. Rpn-1 is the quotient of SLNR by some parabolic subgroup by all the entries except the first column. So this is the second type of candidates. And the third type of candidates, so there are isometries. These are the maps, are the actions where gamma acts through a compact group. So they are morphism from gamma to some compact group, and this compact group acts on manifold M by rotation or something. And conjecturally, this is very rough conjecturally, so under this and that assumptions. So all gamma actions are some kind of combinations between these types. And again, up to some minor defect. You can do some small twist here and there. But these are supposed to be the basic building blocks for gamma actions. Okay, so next, let me state one theorem towards this program. So let me say that it's a very broad program and not much is known so far, and not much is known in general. And usually all the assumptions you need to make some extra assumptions. And typical assumptions would be, say, the action preserves a measure, or the dimension of the manifold is low, or the group is much larger than the manifold, etc. So the first theorem that I wish to state. So this is a joint work with Federico Rodriguez, Aaron Brown, and myself. So let me just say a special case of this theorem instead of the general case. If gamma is lattice inside SLNR, and n is at least 4, which makes the rank at least 3, then gamma doesn't act smoothly on a surface. Okay, let me, yeah, thank you. I cheated a little bit. Doesn't alias through a finite group. So otherwise, just doesn't act at all. So this is a corollary of what we proved, and the main technical intermediate theorem is that so if gamma is in SLNR and it acts in n-2 dimensions smoothly, then it must preserve a measure mu on M, a probability measure. Then this plus a theorem of Franks and Handel. So the Franks-Handel theorem stated that if gamma acts on a surface so in 2 dimensions, preserving mu, then there is a character of gamma into R or into the circle, but this is not the case for such lattices. There is a morphism from gamma to R. Okay, so that's the intermediate theorem, and the idea behind the theorem is that if gamma acts on M, then it will induce a so-called suspension action. It will induce a G action no longer on M, but on some larger space M tilde, which looks like it is a bundle where the fibers are M and the base is G mod gamma. And in order to show that gamma preserves a measure, you only need to show G preserves a measure there. And then let P be the minimal parabolic subgroup of G, preserves a measure. Because it is amenable, then we somehow could show that this measure is also G-variant. This last part is an entropy counting argument. That's complicated. Okay, so okay, I wish to talk about something else, but I think I would stop here. Time is up for me. Thank you.